Example 1 in 7.3 is the integral of 1 over x squared times the root of the quantity 9 minus x squared. Alright, so that's kind of a not pleasant looking integral here at first. Notice there's no trig functions in here, but trig substitution is a possibility because if you look at again at the formula sheet, the square root of 9 minus x squared is of the form square root of a squared minus x squared. So, that's something that could apply here. But before you jump into that, trig substitution technique is real lengthy. You should always see if substitution works first. Just regular substitution from 5-5. So, kind of a candidate for u would be 9 minus x squared, the inside of the composite function. If you take the derivative of that, you get negative 2x. Do a bit of algebra here. X dx, you got to find x in there, and dx is always there, can be substituted with negative d over 2. So you try to do that. There's not an x hanging out, so I made one by multiplying by x over x. So let's see if we can get this to work. We have our square root of u from our substitution. Leftovers in this are x cubed. For the leftovers, remember you have to use the u. You cannot use the du. It's a one-shot deal. So looking at that 9 minus x squared, there's just no way to represent that with a u. And so it's not possible. We weren't able to do it. But it's worth really looking into before you launch into doing trig substitution, which looks like is our only option to evaluate this integral. So we're ready. On that formula sheet again, this is of the form square root of a squared minus x squared. So what that means is, it's a different color here, that we are going to, in the next column it tells you let your x equal a sine theta. So you're told the substitution, the trig substitution to make. Very early on here you have to identify your a. So what we have is 9 minus x squared. That's the form that we identified as part of our integral. And note that that is equal to 3 squared minus x squared, which means our a is 3. So that means we're going to make the substitution of x is equal to 3 sine theta. As part of that, we need to find the dx. And I actually have that as part of step 2. So, or excuse me, step 3. So I guess I should be consistent here. All of step 3 is writing the integral in terms of theta using that substitution identified in step 2. And so looking at the original integral, what we're going to do is we're going to plug in for every x in here a 3 sine theta. Careful though, dx is a package deal. That x there is not like a standalone x. This notation's a package deal dx. dx is something different, so it's not too hard to find, but it's not d with 3 sine theta or something like that. So we do that. To find the dx, all you have to do is take the derivative of the x with respect to theta. So this is Leibniz notation saying that. And what is the derivative of 3 sine theta? It's just 3 cosine theta. And then do a bit of algebra by multiplying both sides by the differential d theta. And we have dx is equal to 3 cosine theta d theta. So that's what we're going to put in for dx. So here's the part in the intro where I said you're going to end up with something more, or not something, an integral that's looking way more complicated than what we started with. But supposedly we're going to be able to evaluate that integral, which of course is what we're trying to do. So on top I'm going to have 3 cosine of theta d theta, substitute in for the dx. Down low I got 3 sine theta in parentheses, squared instead of x squared, and then I have root 9 minus, and then instead of x squared I have 3 sine theta in parentheses squared. So wow, that looks really complicated now, right? Kind of nasty. But again, supposedly we're supposed to be able to do this integral now. I can do it. Alright, get this fraction line. Next thing is what identity is going to apply here, because it turns out you're always going to have to use an identity in order to simplify this thing and do the integral in terms of theta. So you don't have to do it here, but early on it's good to recognize that. It's going to be one of the trig identity, the Pythagorean identities, and the one that's going to apply here is the one sine squared plus cosine squared equals 1, because we have sine cosine stuff in here. So that's just good to have in your back pocket, because it's going to come up if you're doing this correctly. So step 5 is just pretty much continuing with step 3 and starting to do the simplifying, because what you're going to have here is something that's not simplified. The most important thing to simplify is underneath the root. This is where the magic's going to happen, and we're going to see the purpose of doing this, how this is going to work. It has to do with the simplification of that root. So you got to work hard on that. I'm just going to rewrite the other stuff. And I'm going to have 9 sine squared root of 9 minus 9 sine squared. You have to be very careful that you are using your exponent properties correctly to get that 9, or this just doesn't, it shuts down. It doesn't work. Next thing, notice that you have a common factor of 9 down here, and you want to pull that out. I'm going to do a few more steps here than what I would expect you to do and what I'll show later on, just because we're starting out. I guess I can do the simplification as I go. Just get 3 there. So when you pull out the root, you're left with 1 minus sine squared. Now notice with your exponent properties, because you got times over here all the time, you can separate this into square root of 9 times square root of 1 minus sine squared, and square root of 9 is 3. So we can do that. And what we'll have then is, well, I'll write it separate here to start out. Got a 3 coming out, and we have 1 minus sine squared under the root. So the trig identity is going to always have to do with this root part. So looking at our trig identity, what we're going to do here is we're going to solve for 1 minus sine squared, or see that we can do that. So I can do that by subtracting the sine squared term from both sides, and get cosine squared is equal to 1 minus sine squared. So I can substitute in cosine squared for 1 minus sine squared, and the reason why this is the part that makes all this work and worthwhile is then I can simplify and get rid of that root. I have cosine squared, it's going to cancel with the square root, and then lots of good things are going to happen. So this is a really critical step. Now what we got is, I'll put a 9 out front, sine squared, and then kind of showed some of this, but again I'll kind of do the overkill on the work here to start out. The square and square root undo each other, so now we have cosine theta over 9 sine squared theta times just cosine. Pair of cosines cancel, and now what we have is the integral, I can pull the 1/9 out even, of d theta over sine squared. Now we're supposed to be able to evaluate this integral. It's all simplified, and we need to start thinking about this. Well, this one's not ready to go right away. You could start looking at 7.2 and look at the trig integration techniques, but you know, always try to do the simplest thing first. Stop, reflect. Can you write this as an elementary integral for which you're either given the elementary integral or you have it memorized? So a hint here that something like that might apply is whenever you have like a ratio of sines and cosines, or the sine and cosine are underneath a fraction, then there's a different way you can look at it. So the way that you could look at this, or simplified form here, this would be 1 over sine of theta, that quantity squared, and 1 over sine of theta is the same as cosecant. And then you got the square over all. So this is another way to write this integral. So look at your formula sheet, and you probably get really excited to see that you actually have this integral on your formula sheet, or maybe you even have it memorized from Calc 1. But I just decided to give it to you on the formula sheet because maybe you wouldn't have this one, be as familiar with this one. So this turns out to be negative cotangent. The idea here is that the derivative of cotangent is negative cosecant squared. So if you have that derivative rule memorized, that could help you too. But it is given with its integral form. And so we're pretty much done with the evaluation of the integral part. In terms of theta, we're going to have 1/9 times negative cotangent theta, attach your plus c at the end, and we got negative 1/9 cotangent, cotangent theta plus c. Alright, so that's great. We've been doing a lot of work, but we're not actually done. So if you look at the original problem, it was in terms of x. So scroll to that quick. That problem was the integral of 1 over x squared times the square root of 9 minus x squared. And this thing has thetas in it, which is, you know, what is that all about? So we need to put it back in terms of x, because that was the original problem. We were just using this trig substitution in terms of theta as a tool to evaluate the integral. We accomplished that, but now we got to go back in terms of x. So this is what I've called step 6. If it's an indefinite integral like we got going on here, then we're going to do the stuff with the triangle. And we're going to use that answer, but for now you're going to kind of take a break from that negative 1/9 cotangent theta plus c and go back to the beginning and identify your original substitution. What was it? Probably don't remember because it's been a while. You work on these problems. So go back and look, and you'll see that it's x is equal to 3 sine theta. So you're just going to use that and construct this triangle, this right triangle, that jives with that. So what we do first is do a little bit of algebra and divide by the constant up front. And then we're trying to find theta. Or not try to find theta, but we write down the theta as one of the acute angles here. I always use this one here, but there's other options. And so x over 3 is what we're going to label on this right triangle. Sine of theta is opposite over hypotenuse. So that means that our opposite edge in this right triangle is going to be x, and the hypotenuse is going to be 3. Now automatically you can just go and find the missing edge, because it turns out you're going to need that always. And so use the Pythagorean theorem for that. Maybe you can do it in your head, or if not, you could label a dummy variable like z and write out the legs squared, or z squared plus x squared equals 3 squared, and then solve for that dummy variable. Whatever you need to do. But what that missing edge is square root of 9 minus x squared. It happens to also correspond with the original form that you started with. Those are always the same. Anyway, probably just best do it here. Now, go back to your answer, and it turns out you can now write your answer in terms of x using this right triangle you constructed. So the answer was -1/9 cotangent of theta plus c. So now you need to remember what cotangent of theta is in terms of the lengths in this acute right triangle. Well, I remember that cotangent is 1 over tangent, so it's a reciprocal of tangent. Personally, that's how I remember it. Lots of ways to do it. So instead of having opposite over adjacent, it's going to be adjacent over opposite. So looking at my triangle with the theta in the position I chose to go with, adjacent is going to be like the z thing that I found, 9 minus x squared underneath the square root, and then my opposite is x. And of course, don't forget constants like I just did. This was -1/9. Just rewrite it. So -1/9, and then adjacent again was square root of 9 minus x squared, and opposite was x plus c. Pretty much done. So negative root 9 minus x squared over 9x plus c. And that's it. Long problems.